All right, so this is going to be 5.5 part 3. We're going to take a look at using that substitution technique that we were doing earlier to find the value of a definite integral. Remember, definite integrals are these guys right here with limits of integration where the answer is going to be a number. There are two methods. One technique, kind of an old school technique. If you have an older instructor, they'll probably do it this way because they haven't changed in 50 years. Is to evaluate the indefinite integral first and then use the fundamental theorem on it. I think that is a waste of time because it makes you do like 3 extra steps. And why? If you learn nothing at all about me this semester, you've learned that I'm lazy. And so if there's a faster way to do it, I'm going to do it the faster way. All right, so let's take a look at what we're going to do. We are going to be using the substitution rule for definite integrals. Okay, so I'm going to zoom in on this. And so basically what we're going to say here is that if we are handed an integral to perform and we recognize that the integrand is something that fits the form for substitution, that is, it contains a composite function and the derivative of the inside piece of that composite function, okay? If it contains that setup, then we are going to use substitution on the integrand, and this is the substitution on the integrand. But the other thing to make note of is if I change my variable from x to u, then these limits of integration here also have to change because those limits of integration in the original integral were based on the variable being x. If the variable is now u, we have to change them. And how do we change them? We change them by using the substitution piece from our substitution here, the u statement. And when we do one, it'll be more clear, right? So let's start right here with this one. Now, we've actually already done this integral before, but it was an indefinite integral when we did it before, right? So it's going to walk through it. Here's my composition. So there's the inside piece. So I'm going to make the argument that u is equal to 2x plus 1. And then the differential du would be equal to 2 times the differential dx. I don't have 2 dx, I just have plain old dx. So I'll say that 1/2 du is equal to dx, and then I'll perform the substitution. The substitution then becomes the square root of u times 1/2 du. But now what I need to do is I need to figure out what's going to happen to the original limits of integration. What's that 0 going to become when I change from x's to u's? And that 0 is going to become 1. How did that happen? Right here. Right? If u is equal to 2x plus 1, if u is equal to 2x plus 1, then u is going to be 2 times 0 plus 1, which is 1. And so then what will the upper limit of integration become? Well, that upper limit of integration is going to become u equals 2 times 4 plus 1. 2 times 4 plus 1 is 9, so it becomes the integral from 1 to 9. Now that I've done the substitution and both things that were supposed to happen happened, that is all the x's turned into u's, and now I have an integration that I can probably perform, I'm going to go ahead and perform this integration. I'm going to move the 1/2 out in front. So I have 1/2 times the integral from 1 to 9 of u to the 1/2 du. Okay? That's going to give me 1/2 times 2/3 u to the 3/2 evaluated from 1 to 9. I'm going to take the 2/3 and the 1/2 and put those together, and that's going to give me 1/3 times 9 to the 3/2 minus 1 to the 3/2. 9 to the 3/2 is 27. Okay, the denominator of 2 is a square root. Square root of 9 is 3, and then 3 cubed is 3 times 3 times 3. 3 times 3 is 9 times 3, 27, minus 1, and I get 26/3. Okay, so I performed substitution. Now, the one thing that is significantly different in this is there is no step anywhere down here at the end where we switch back from u's to x's, because we don't need to. We took care of that need right there when we changed our limits of integration. Right? All right, let's take a look at another one. Right? Here's another definite integral. My job is to perform this definite integral. I'm looking at my integrand and I'm seeing two things multiplied together. One of them is composition, so I think substitution might be the way to go because I can't do it as it sits. So I'll make the statement that u is equal to x squared plus 1. Then the differential du is going to be 2x times dx. I just have x dx. I don't have 2, so I'll just modify that statement. I'll divide through by a 2. So 1/2 du is equal to x times dx. And now I've got what I need to do my substitution. This right here is right there, so that's just going to become a u. And the x dx here and here is just going to become the 1/2 du. And so now I get the integral of u cubed times 1/2 du. And now I got to figure out my limits of integration. The lower limit of integration was a 0. What will it become? Well, I'm going to put that 0 into this u statement here. 0 squared is 0 plus 1 is 1. So my lower limit is 1. My upper limit of integration, what is it going to become? I'm going to put that 1 into the u statement. 1 squared is 1 plus 1 is 2. And this becomes the integral from 1 to 2. Okay? With a little bit of work, I can show that that is 1/2 times 1/4 u to the 4th from 1 to 2. So that's going to give me 1/8 times 2 to the 4th minus 1 to the 4th. Okay? 2 to the 4th is 16. 16 minus 1 is 15. So I get 15/8. And so the value of that integral is 15/8. Okay? So I'm finding the values of integrals using a technique called substitution. These are definite integrals. And when I do a definite integral substitution problem, I have to make sure that I change those limits of integration. I will tell you that the number one mistake that I will see on this problem, and that you will find yourself making, is you'll forget to change those limits of integration. And you'll get to here, and you'll have done your calculus correctly. You'll evaluate, and you'll evaluate correctly, but you'll get the wrong answer because you're evaluating for the wrong limits. So when you get one of these problems wrong, and it's going to happen, I do it myself sometimes, first thing you should check is, oh yeah, substitution. Did I change my limits correctly? Right? All right, there's got to be more. There's always more. Ah, here's another one. Awesome. Ooh, I don't like how this one's written, so I'm going to rewrite it. I'm not changing anything. I'm just rewriting it so that it feels more comfortable. That looks a little better. I'm seeing composition. So I'm going to try substitution because I don't know what to do with a -2 exponent otherwise. So let's see. If I say that u is equal to 3 minus 5x, then the differential du would be equal to -5 times dx. So I'm liking some of what I'm seeing. I'm seeing this right there that I can do a substitution on, but I'm only seeing dx, not the -5 dx. So I'll divide by -5. Remember, you can always fix a missing coefficient, but you can't fix a missing variable. That's another issue. So -1/5 du is equal to just dx, and now I can do that substitution because it matches, right? So making that substitution, so here I am at this point. I've got the integral of u to the -2 times -1/5 du, but what are my new limits of integration? Well, my lower limit of integration was a 1. What will it become? Well, if I put a 1 into the u statement, 5 times 1 is 5. 3 minus 5 is -2. Right? My new upper limit of integration. Right? My new upper limit of integration used to be 2. What will it be now? I'm going to put that 2 into the statement here, into the u substitution statement. 5 times 2 is 10. 3 minus 10 is -7. And so my new integrals from -2 to -7, u to the -2, -1/5 du. All right, I'm going to take the -1/5, move it out in front. So I got -1/5 times the integral from -2 to -7 of u to the -2 du. I'm going to snooze this. And now it's time to integrate. Add 1 to the exponent. So I've got -5 times. Add 1 to the exponent, flip it. So -1 times u to the -1 evaluated from -2 to -7. So let's see, what's that going to work out to be? Let's see, that's -1/5. Wait, I'm going to pull this negative out there and just make that a +1/5 to make this easier. and then 1 over negative 7 minus 1 over negative 2. Because remember, a negative 1 exponent just means 1 over. So let's see, 1/5 times 1/2 minus 1/7. Let's see, 1/2 minus 1/7. I'm sure you just know that off the top of your head is 5/14. 1/2 is 7/14. 1/7 is 2/14. 7/14 minus 2/14 is 5/14. And I get 1/14 in the end. So the value of my integral is 1/14. Hey, how do I check my work on these things? I mean, I don't know that I'm doing these things correctly. I'm getting answers. How do I know if they're right or not? Well, there actually is a pretty simple way to check these. Let's see if I can find it real quick. Let's see, File Explorer, Documents, Wabbit, EMU. If I just use my calculator, I can actually, let me close that one. Let me close that one. Why are there so many of these? Oh, okay. I can pretty easily check my work. So I'm going to go back, quit out of there, go back to my home screen. Let's see. I'm going to do an integral from 1 to 2 of the fraction 1 divided by the quantity 3 minus 5x. Close that quantity and square it. And this is dx. And I chew on it for a while and it spits out 0.017. And I think that's 1 divided by 14 now. Looks pretty good. Yeah, what do you know? I got it right. Hey, wouldn't that have been nice to know a while ago that you could use your calculator to check these? All right. Now, I am in no way arguing that you should use your calculator for every single one of these problems, because being able to perform these calculations by hand is a necessary skill for Calc 2. So if you show up, if you roll up into Calc 2 not being able to do these problems, you are going to be hurting, and hurting mightily. All I'm simply saying is this is a way that you could check your work. This is the way that you could ensure that you're doing these problems correctly. Okay? All right, so back to this. How many more we got? Oh, just one more. And this one's a doozy. You're going to love it. All right, so here we got the integral from 1 to e of the natural log of x divided by x dx. Now, something about this is talking to me. So I'm going to rewrite this, and I'm hoping that when I rewrite it, you'll see what I'm seeing. Do you see a function here and its derivative there? Substitution. U natural log x du 1 over x dx. Everything is going to substitute perfectly. I get the integral of u du. What's my new lower limit of integration? What does 1 turn into? Well, if I put 1 into this statement right here, the natural log of 1 is 0. Well, that was an ugly 0. And then if I put in my new upper limit for integration, e, what does e turn into? Natural log of e is 1, so from 0 to 1 of u du. The integral of u is 1/2 u squared. Evaluated from 0 to 1, that's 1/2. And guess what that does for us? This brings us to the end of section 5.5. Not only is this the end of section 5.5, but this is the end of the semester. This is our last section. And kind of bittersweet. I'm happy that we're done. I'm sad to see the semester go. Hopefully, everything is going to work out nicely for you. I have another sheet of a whole bunch more substitution practice. And I'm going to make a video for that as just an extra one once we get done with the live tutoring session, which is happening in like 5 minutes or so. Okay? All right, so at this point, you should be able to do everything that you need to be able to do for the entire semester. So get busy, get that work done, take those exams. You only have a few days left. As of today, I'm making this video on Tuesday morning, so you have 13 days left. Please, 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 please don't wait until the last minute. All right, have a good day.